Okay, thanks, session chair. Hi everyone, thank you for being here to listen to our talk. My name is Mengming. I'd like to introduce our work, Profile Guide Temporal Prefetching. Other authors are Qijun, Zhang, Yichuan, Wenji, Fang, Yongqing, and Zhiyao. Okay, let's start. First, I will introduce the background and motivation behind our work. Temporal prefetching focus on temporal patterns, which has two characteristics. First, the temporal pattern is irregular, which means that normal prefetchers are ineffective for the temporal patterns. Second, the temporal patterns repeat across time. For example, in this slide, at T1, a PC accesses the S0, S1, S2, S3, S4, and at T2, the same PC accesses the same memory access address. So if we remember the memory addresses at T1 and we can prefetch them at T2, that's the core idea of the temporal prefetching. This slide shows the idea of temporal prefetching. It mainly includes two stages, the training stages and the prediction stages. In the training stage, the temporal prefetcher will record the address correlation in its metadata table. For example, the PC1 accesses the address 1, address 2, and address 3, and each record the successor of the address 1 is the address 2, and the successor of the address 2 is address 3. Then in the prediction stage, when the address 1 comes to the temporal prefetcher, it will accordingly prefetch the address 2 and then the address 3. The state of the art temporal prefetcher always employs a big metadata table and share space with last level cache. The maximum size of the metadata table is about 1 megabyte. Then I will introduce the challenges of temporal prefetching. The left side of this slide shows a figure in article published in ISCA' 2025. It classifies all memory instructions into 4 types. The non-temporal memory instruction, the stream spatial instructions, real recurrence instruction, and frequent recurrence instructions. Only a small subset of memory instructions should be handled by the temporal prefetching. So the temporal prefetching face significant noisy data. According to our experimental results, this noisy data always larger than 1 megabyte for many workloads. So if we store this non-temporal metadata in our metadata table, we would waste precious on-chip storage. And if we issue prefetch requests with this non-temporal metadata, we will cause cache pollution. As a result, the core task of temporal prefetching is metadata management or the metadata table management. In other words, we should only make the temporal prefetching focus on the frequent recurrence PC. In order to enhance the metadata table utilization, previous works proposed several management strategies like the insertion policy, replacement policy, and resizing. The insertion policy will filter out all non-temporal metadata before inserting them in the metadata table. And the replacement policy will choose useless metadata when the capacity of the table is full. And the resizing operation will dynamically adjust the size of the metadata based on the workload requirement. The main issue of previous metadata management strategies is that they achieve little performance gain while introducing non-negligible or significant storage overhead. For example, the Trij use state-of-the-art replacement policy in normal cache to manage the metadata table, but it only brings about 0.25% while introducing over than 10 kilobyte storage overhead. The similar trend occurs in other metadata management strategies like the insertion policy and the resizing. Next, we will use a case study to show why the previous metadata management strategies are inefficient. The pattern conf is used in triangle to filter out unsuitable metadata. The logic behind the pattern conf is that if past memory accesses are observed as non-temporal patterns, the future memory accesses are not likely to be temporal patterns, and will accordingly prevent metadata insertion. However, as we will introduce later, the past program behavior may not indicate the future program behavior in the context of the temporal prefetching. The left figure shows a metadata access pattern in a workload in spec CPU benchmark, the Omnet PP. The pattern conf decrease when encountering useless metadata accesses. The red point in our figure. As shown, and it will increase for the blue point, the useful metadata accesses. As shown in the bottom figure of this slide, metadata accesses are highly variable, characterized by interleaved useful metadata accesses and useless metadata accesses. By observing initial metadata accesses, the pattern conf mistakenly considers the current PC does not show temporal patterns and filter out subsequent metadata accesses or metadata insertion. Consequently, the pattern conf or the insertion policy in the triangle inaccurately manage all blue points in our figure. Next, I will introduce our solution Prophet, which leverages the profile-guided solution for the metadata management. Prophet is the first profile-guided solution for temporal prefetching. It profiles the complete program execution to establish management strategies. Compared to the highly variable metadata access patterns, the profiling data, which is located in the center of this slide, is relatively more regular. Prophet can tailor different management policies for different levels of profiling data, achieving more accurate metadata management. Beyond the temporal prefetching, Prophet overcomes several challenges in traditional PGO solutions. First, it's a lightweight profiling solutions, which means that we does not use any trace systems or memory trace systems for profiling. We only use PMU to collect counters to profile the target binaries. Second, our scheme is adaptable, which means that through repeated learning, our scheme can achieve optimal performance for encountered inputs. In contrast, the prior solutions can only be effective for the latest encountered inputs. Furthermore, Prophet is compatible with existing runtime solutions like the hardware temporal prefetcher triangle. So the designer can switch to the runtime temporal prefetcher when needed. For example, if a program is really wrong, you can simply use the runtime solution to save additional profiling overhead. Prophet, in summary, Prophet is a counter-based PGO solutions. It profiles program execution counter to generate hints, inject hints into the original boundaries, and craft PC level and binary level metadata management strategies, and can learn counter from different program inputs to make adaptable binaries. Prophet includes 3 steps: profiling, analysis, and learning. I will introduce them as follows. At step 1, profiling, this step is responsible for collecting program counters relative to temporal prefetching. We want to profile each memory instruction's adaptability to temporal prefetching. So we configure the temporal prefetcher with a simplified version. We disable the insertion policy, the resizing, and set the prefetching degree to 1. Then we use the PMU system to collect the counters. At step 2, analysis, Prophet leverages the collected counter to generate hints. There are 2 types of hint, the PC hint and the CSR hint. The PC hint is used to guide the insertion policy and the replacement policy, and it was bounded to each memory instructions. And the CSR hint can globally apply to the whole binary, and we only use 1 CSR hint for 1 binary. Finally, at step 3, Prophet sample counters from different program inputs, and we develop an algorithm to merging the old counter and the new counter. After merging them, we use the merged counter to regenerate or update the PC hint and the CSR hint. This hint can be effective for the new inputs and the all encountered old inputs. Finally, we introduce the evaluation results of our work. We adopt a system configuration like the triangle, which is published in ISCA 2024. Then we compare our work to 2 representative prefetchers. One is hardware temporal prefetcher triangle, and another one is software indirect prefetching RPG2. This slide shows our performance evaluation results. Prophet outperforms the hardware temporal prefetcher triangle by about 40% and RPG by about 33%, while it's introducing only about 5% derun traffic. Additionally, Prophet introduced negligible PGO overhead. For each profiling, Prophet only requires 3 PBS events and 1 standard PMU event, introducing less than 2% profiling overhead. Furthermore, we only profile the program once for 10 to 100 program executions. For the analysis overhead, Prophet only requires less than 1 second to handle the collected counters and generate hints. Finally, for the instruction overhead, Prophet introduced about 100 hint instructions. Compared to the billions of instructions in the space CPU benchmark, these introduced hint instructions are negligible. We also evaluate Prophet's ability to learn from different program inputs. With only 4 rounds of learning, Prophet can achieve near optimal performance across 9 GCC inputs. We also evaluate individual features proposed by the Prophet, like the insertion policy, replacement policy, and another runtime feature which we don't cover in our presentation. And we find that all features contribute to Prophet's performance improvement. And the Prophet insertion policy is most effective for reducing DRAM traffics. Okay, let me give a conclusion. Prophet is the first solution that applies PGO into temporal prefetching. Beyond temporal prefetching, Prophet is adaptable, lightweight, compatible, overcoming several challenges in traditional PGO methods. Third, Prophet outperforms prior state-of-the-art work like the triangle and the RPG2 across extensive configuration and benchmarks. That's all my presentations. Thank you.